Hello dear students, welcome you all once again. I am Meghamala, working as assistant professor from EC Department, Institute of Aeronautical Engineering. And so far we have discussed about the definitions and terminologies from module 1, that is Verilog as HTL. And now in today's class we will discuss some more definitions from module 2, that is gate level modeling. So our module 2 is all about the gate level modeling. In the gate level modeling we have few definitions to be discussed, okay? And so coming from the for the first definition, as we go with this, define gate level modeling. So what is this gate level modeling? Gate level modeling is used to implement the lowest level modules in a design, such as multiplexer, full adders, etc. So here, this Verilog has a gate primitive for all basic gates. So basically, this gate level modeling, it deals in order to build some basic building blocks, all that we need is gates. So all such gates we can get it from the Verilog library. So all the gate primitives can be obtained from the Verilog library. So here different modules that we can easily design based on this gate level modeling. They are multiplexers, full adders, okay, multiplexers, full adders, decoders, encoders, and all these things. So gate level is used to implement the lowest level modules in the design. So as we say that we have four kinds of modeling styles: behavioral modeling, gate level modeling, data flow modeling, and switch level modeling. So out of this, among these four modeling styles, the third modeling is all about the gate level modeling. So here in this gate level modeling, we are going to design the circuits based on the gates. So all the gates can be obtained from the Verilog. Gate primitives can be obtained from the Verilog library. Okay, then what are gate level primitives? So what are the gate level primitives? So gate primitives are defined in the Verilog. Okay, so in order to build some circuit, some digital circuits or else some electronic devices, we need gates, right? So all the gates can be obtained from the Verilog. So all the gates which are in the library, Verilog library, we can easily access all such gates. Then which are ready to use? So the gates which are already present in the Verilog library, they are ready to use. Okay, whenever we need, we can access it from the Verilog library. Then they are instantiated like modules. So as I said you, in order to build some major blocks or else in order to build some electronic devices, we need the building of such electronic devices can be happen with the help of the gates. Okay, so all the gates which are present in the library is nothing. From the Verilog library, we can have an access to take the gates from the Verilog library. So we can easily use it. Okay, we can easily access it, and they are instantiated like module. For example, I'm going to design some half adder. So in this half adder, I'm going to use two kinds of gates. One is OR gate, and the second one is AND gate. Okay, and the second one is XOR gate. So AND gate and XOR gate can be obtained. Okay, I can make use of AND and XOR gate from the Verilog library. Okay, from the Verilog library, we have great primitives like. So from the gate primitives through the Verilog library, I can easily make use of this AND and XOR gates. Okay, so here what am I saying is, as I'm considering one of the gate from the Verilog library as AND gate, so that AND gate I can instantiate it, or else I can give that a particular AND gate or XOR gate as a name module. So that AND gate acts as a module to that. So in order to design some half adder, how many kinds of modules that we are using is AND module and the XOR module. Okay, for example, when you are writing a code, you have to mention like this module. Module is a keyword, and you are designing the half adder, right? So module is a keyword, a half adder, and the port list, isn't it? So this port list consists in input ports, output ports, and in-out ports, right? So here my model is all about the half adder. So from this half adder, how this half adder is formed, or is how this half adder is coming into a structure, is because of I'm using the two modules in the sub module, that is AND is a sub module and XOR is a sub module. So my sub modules are AND and XOR. So they are instantiated like modules. Then there are two classes of gate primitives. So here through the gate primitives in the Verilog library, with the help of gate primitives, we can access the different gates in order to design the basic building blocks. So basically, there are two classes of gate primitives we have in the Verilog library. They are multiple and the single input gate primitive. Multiple input gate primitives and the single input gate primitives. So here, as the name indicates, multiple input gate primitives. So these gates are nothing but we can give the inputs, like 2 or more inputs can be given to such gates. Okay. So the name indicates like multiple input gate primitives, and some gates we can give only single input can be given. So they are comes under the single input gate primitives. So multiple input gate primitives includes AND, NAND, OR, NOR, XOR and XNOR. So obviously AND, see, more than 1. So it is a double input. Okay. And when it comes to NOT gate, so this is a NOT gate. So it's a single input. Single input gate primitive is nothing but the NOT gate, and the rest of all the gates are comes under multiple input gate primitives. Okay. So in the gate primitives, we have discussed like gate primitives can be accessed easily from the library, and they are instantiated with the help of a name given by module, and they are categorized into two types. One is multiple input gate primitives, and the second one is single input gate primitives. Multiple input gate primitives are nothing but AND, OR, NOR, XNOR and so on, because they have more than one input can be given. And coming to the single input gate primitives are nothing but only one input can be given as a input to that particular gate. And so we can give an example for single input gate is NOT gate. Then coming to define rise time. Okay, so what is this rise time? Rise time is nothing but it is equal to the time taken by gate output transition to 1 from another value 0, X or Z. Okay, so now this rise time is nothing but whenever a steep curve is taking its position from 0 to some 1 position. Okay, from 0 to some 1 position, what happens here? The delay is mentioned as time delay, right? And then what is fall delay? Fall delay is nothing but when it is transition its position from 1 to 0. Okay, transitioning its position from 1 to 0 is nothing but fall delay. Then, so here, when the transition, the output transition, when it is taking place from 0 to 1, okay, to 1, towards 1, and another value, it could be of 0, X and Z. So likewise, fall delay is nothing but it is quite opposite to the rise delay. So it is equals to the time taken by gate output transit from to 0. So it is from 1 to 0, it is transiting, isn't it? It is transiting from 1 to 0. So it is called as the fall time. And one more time, delay. One more delay we have discussed here in this module 2, gate level modeling, is all about the turn off delays. So what is this turn off delay? Turn off delay, it is equals to time taken by gate output transit 0 to high impedance. So when it is going from 0 to high impedance, 0 to some impedance, 0 to Z, okay, which is a saturated point. If it is going towards saturated point, then it is called as a turn off delay. So here if you observe, this is a graphical representation of rise time, fall time and turn off delay. So there are 3 ways to represent this gate delays. One is 1 delay, 2 delay and 3 delay. So before we go in that, if you observe the diagram, if you observe this timing diagram, you will be able to understand easily. So if you observe here rise time, this is a T rise. So it is taking its position from 0 to 1. So it can take from 0, X or Z. And this is a fall time. So fall time is from 1, X or Z to the 0th value. And then coming to the turn off delay. So this turn off delay is when it is taking, when the transition, if it is going towards the high impedance state, okay, towards the high impedance state. That means from either it could be 0 to high impedance, 1 to high impedance and unknown to high impedance. So this is nothing but the turn off delay. So here, coming to the displaying of orders, there are the 3 formats to be represented as per the delays. So if you are going for 1 delay format, so remember in the 1 delay format, in the coding part, if you observe or else if you write the delay with only 1 delay, okay, delay we are representing it with the hash, and if the delay is specified only 1 delay, and this is a module name and this is a port list. So this is a port list, name of the module, and this is a delay number, and this is represent nothing but a delay. So it is a number representing of the number. So we are saying it is a single delay specified. Why we are saying it is a single delay specified means here we have displayed only one delay. So it is named as one delay format. And coming to two delay format, in this two delay format, we will be representing two delays. One is rise and fall time. So if you observe here, this is a rise and fall time. Right? So this is 1 and this is 2. So it is nothing but the two delay format. Specifying the two delay format is like how it goes. And then coming to the three delay format. In this three delay format, you see rise, fall, and turn off. So all the three delays, if you are considering in your coding, okay, as per the specifications, if you are considering all the three delays in your coding, then this is how the representation takes place of the three delay format. Okay. Then what are the user-defined primitives? So what are the user-defined primitives? These are nothing but there are new primitives, small components, and used exactly the same as the built-in primitives. Okay, so this user-defined primitives. So the name says that user-defined primitives. So some primitives where the user can define by himself. Okay, so in order to create some module, or also in order to create the exact module which is obtained by the other. So here there are new primitives. Under user defined primitives, we can see that there are new primitives which are consist of small components and are used exactly the same as the built-in primitives. So however the built-in primitives we are using, in the same fashion we can go for this new primitives which are user defined primitives. So the number inputs may be limited. Okay, so these primitives, it can be of limited numbers. Okay, and there are at least 9 inputs for sequential UDPs and 10 for combinational UDPs. So user defined primitives are categorized into two types. One is One is sequential UDP. So in the sequential UDP, the primitives are considered to be, the maximum number of primitives are considered to be 9 inputs. Okay, for when it comes to the combinational UDPs, the maximum number of primitives can be they goes as 10 inputs. So this is the difference between your sequential UDPs and the combinational UDPs. So UDP begin with the reserved word primitive. Okay, so user defined primitives. When you are supposed to write a program with respect to the user defined primitives, then you have to make sure the module name, or else we have to make sure the keyword that you have to mention is about the primitive, and it should end up with the end primitive. If you are starting your code with the module, then you must end with the end module. So here in the UDPs, if you are starting with the primitive, you have to start with the primitive. Okay, user defined primitives. So if you are starting with a primitive, then your code must end as end primitives, right? Then port and terminals of primitive should follow, and then followed with the port list. In this port list, terminals of primitives can be mentioned in the port list. And then UDP should be defined outside the module and end module. So outside the module and end module, the primitives can be defined. The primitives can be defined outside the module and as well as the end module. So here in this particular example, if you observe, we are starting the code with the primitive is a keyword, right? So primitive UDP name, and this is a port list. So primitive list or the port list. Then port declaration, and now we are declaring the port. So what sort of inputs and outputs that we have? Okay, next. So register output. Okay, register is the output net, and initial output is equals to initial value. So the primitives goes with initial inputs like I0 to initial value, and then goes with the table. So this table consists of the truth table, and as we have started the table, which is having the truth table, and so we are ending it with the end table, and we have started with the keyword primitive, then finally ending up with the end primitive. So this is how the code will be written when it comes to the user defined primitive. So your code must be vary when you're considering the sequential UDPs or combinational UDPs. But remember that out of the module and end module, all these things can be written. Okay, they are not supposed to be right in between the module and end module. So UDP symbols, values and inputs and output signals are indicated using the following symbols. So these are the few symbols pertaining to the user defined primitives. So these are the symbols 0, 1, X and all. So we know 0 is logic 0, 1 is logic 1, and X is nothing but the unknown variable or its unknown values. It could be either 0 or 1, and question mark is about logic 0, 1 or X. It cannot be the output of any UDP. So if you are finding in the question mark, it's nothing but it cannot be any output. It cannot be any UDP, user defined primitive. It is something which is out of context. Then a small dash, no change. Okay, it's no change. It's about no change. And if it is AB, change in the value allowed from A to B. If you have any changes, alterations can be occurred to be made in between AB, then you can write change the value AB. Otherwise, A or B, either 0, 1 or X. If there is an changes could be made, then you can represent if the changes. So if you want to, if there are 4 primitives, so if you want to change between A and D, so you can go with this AD or else AC, AB, like that. Then star, same as double question mark, indicates any change in the input value. So if you want to change anything with respect to the input values, then you have to use the symbol. And then R is same as 0, 1, rising edge of the output. So R is the rising edge of the output, and the falling edge of the output is, rising edge means 0 to 1, right? 0 to 1, 0 and 1. So this is rising edge, and falling edge is from 1 to 0. So this is a falling edge. So falling edge we represent with 1, 0, and then P, potential positive edge, either if it is from 0 to 1 or from 1 to 0 or 0 to X, and then N is nothing but the potential of falling edge. So these are the few symbols that we can see in the user defined primitives. And define combinational user defined primitives. So what are these combinational user defined primitives? We say the number of inputs can be given considered for this UDP are 10. For sequential user defined primitives, the number of possible inputs can be considered to be as 9. So define the combinational user defined primitives. So what are these combinational user defined primitives? Are where they are defined where the output is solely determined by logic combination of the input. So here the output depends only on the logic combination of the input. Logic combination of the input. The output purely depends. It purely depends on the logic combination of the input. So here we see that there is a code pertaining to this combinational UDP. So we say that the number of inputs can be given to this combinational UDP is minimum 10. Okay. So primitive mux, the name of the module is mux. These are the port lists. So in the port list, obviously the mux will have the selection lines output A and B. Output is represented as out, initialized, and then input is selection lines A and B. And now we'll come across a table. So in this table, obviously, with respect to the selection lines, right? With respect to the selection lines, the output is determined. So our selection lines, if it is question mark, if both A and B are 0 and 1, the output is observed as 1. So likewise, in the table, with the help of the multiplexer table, that means what the output is purely depends on the combination logic of the input. So here the combination logic goes as per the selection lines. Selection lines A and B, right? If the selection lines is 0, okay, if it is selection lines is 0, the output is observed as 0. If selection line is 1, the output is observed as 1. So there is a logical input. With respect to the logical inputs, the output is observed. And then finally ending up with the N table and the N primitive. So this is nothing but the combinational, what do we say, user defined primitives. Then sequential user defined primitives. And now sequential user defined primitives, it is if the UDP output is declared as register. Okay, if the UDP output is declared as register, the initial power up state for sequential UDPs can be defined with the initial statement. Okay, and there are two kinds of sequential UDPs. So here, if you are representing your module with respect to the register, okay, register is nothing but it is a variable pertaining to the net. From the net list, we can obtain this register. Okay, it is just a variable. So in the sequential UDPs, the maximum number of inputs can be given as 9. Okay, and then the sequential UDPs are again categorized as level sensitive and as well as the edge sensitive. We all know what is level and edge sensitive pertaining to the flip-flops based on the clock signals, right? So level sensitive sequential behavior is represented same as a combinational behavior. So there is a similarity if you are going with the level sensitive and as well as the combinational behavior. So except one thing is that the output is declared to be as register type. So obviously the output is declared in terms of registers. Why? Because in the sequential UDPs, the output we are declaring with respect to the register. So here the output is declared to be as register, but the rest of the thing we can compare it with the combinational behavior, right? Then there is an additional field in each table entry. So also in the table entry, there is an additional thing that we can observe if you are going as per the level sensitive UDP. And this field, this new field represents the current state of the UDP. Okay, so the next state or the next state which is present in the table entry, and that particular column we can state the current state of the user defined primitives, and the output field in the sequential user defined sequential UDP can represent the next state. So the in the table entry, the one column is only meant for the next state of the primitives, right? And this table will consist of the inputs, outputs, and as well as one more column which is present only that is meant for the next state. So this is about the level sensitive and the edge sensitive primitives. And level sensitive UDPs, as I said we can see a similarity between the similarity with respect to the combinational UDP. So the level sensitive behavior is represented the same way as combinational behavior, except the output is declared in terms of register type, right? So here in this coding, we will observe that the primitive D-latch, okay, we have considered the D-latch module. So input port, output and clock. And here we are representing the input output separately in the statement wise. And then if you observe here, the output is Q, right? So the output we are representing or is declared with respect to the keyword or is with respect to the word register. So register Q, and in the table if you observe, we know that Q and D are the inputs. Q and D are, see, this is a Q, okay, and this is in the latch, this is a D, this is a Q, and here it is a clock signal. So here, but in the table, as I said in order to observe the next state, okay, in order to observe the next state, in the table we have a separate column only meant for the next state. We have the input Q, input D, and the clock signal Q, clock signals clock and Q, and here Q plus is nothing but meant for the next state. So based on the input, based on the clock signals and as well as the input, the output is observed with and from the output we can easily observe the next state as well. And finally ending up with the end table and then end primitive. Coming to the edge sensitive UDPs. So edge sensitive UDPs, see here in level sensitive UDPs, the inputs and current states values are sufficient. They are sufficient to determine the output values. Okay, they are sufficient to determine the output values. Why? Because there's no point of going for the next stage. So that's why we are saying that they are sufficient to determine the output values. But whereas in the edge sensitive UDP, it differs that it changes in the output. It differs that changes in the output are triggered by specific transitions of the input. So here in the edge level UDPs, we are observing that there is one more column meant for the next stage Q plus. If Q is our output, Q plus is meant for the next stage. So here the transitions of the input goes as with respect to the output and as well as the next state. So the D flip-flop is modeled as Verilog user-defined primitive. Okay, so this is the example pertaining to the D flip-flop. So primitive D flip-flop, obviously the D flip-flop consists of the input D with respect to the input clock signal and output as Q. So again representing or initializing the inputs and outputs separately. So here register Q. Okay, we are instantiating the output in terms of register Q. Then table goes like this. So this table consists of clock signals. D is the input, clock signal D as input, Q as the output, and one more signal, next signal, right? Next signal as Q plus. So based on the clock input and the clock input and as well as the one of the clock and input, we'll be observing the output, and also the next state can be clearly observed. So here if you observe, this is nothing but question mark and 0, right? So here So here we say that once again. We can ignore negative edge of the clock. So how can we are saying that it's a negative edge of the clock? The negative edge is representing as 0 and question mark is meant for the negative edge, and 0 and 1 are meant for the positive edge. So for the negative edge of the clock we can ignore, and we can consider the positive edge of the clock, and finally ending up with the end table and end primitive. So this is how we can we have to write the code when it comes to the sequential UDPs or in the sequential UDPs, when it comes to the level sensitive UDPs and edge sensitive UDPs. Only in the edge sensitive UDPs, the output, another output pertaining to the next state can be considered in the table. Whereas in the level sensitive UDP, another output is not to be considered. Only one output can be considered, and it can be written in form of table in the program. Then coming to the gate delay. So we all know that what is a delay. Delay is meant with respect to the time constraint. So it is a time constraint. If you are giving an input, if the input is making its transition with some delay, obviously you will see some delay at the output as well. So the gate delay declaration specifies a time. It specifies a time which is needed to propagate a single change from the input of a gate input to its output. So obviously it just makes a transition with respect to the time. As per the input, you will see some delay at the output as well. So the gate delay declaration can be used in gate instantiations. So for example, we can represent the representations of gate delays can be observed like this. And is the name of the module, and delay, we are representing the delay using the symbol ash. So delay of 1 nanoseconds, average 1 some seconds, and gate is the name of the module, and then port list 0 or else output input 1 input 2. Okay, so but the gate delays are represented in terms of ash and some number. If its delay is going as per the 10 nanoseconds, then 10. Actually, if it is 20 nanoseconds, 20. And then every digital gate and transistors cell has a minimum, typical and maximum delay specified based on the process node, and is typically provided by libraries from fabrication foundry. So here if you observe, this sentence is talking about, we'll observe some delays. Okay, so that delays, it could be in terms of minimum delay, maximum delay or typical delay. And all such delays can be provided in the library from the fabrication foundry. So from the fabrication foundry, all the delays can be easily observed, and we can give them a range based on the delays. Okay, it could sometimes it may go the maximum delay, sometimes minimum delay, and the typical delay. And for rise, fall, and turn of delays, there are the 3 values. So for each rise time, fall time, and as well as a turn of time, we can have values based on the minimum, type, and maximum. Okay, they are specified and stand for minimum delay. So if for the rise delay, we can also have a variables, or else we can have these values: minimum value, maximum value, or typical value, and so on the other 2 delays as well. So the minimum delay, min is meant for the minimum delay that the gate is expected to have. So here the gate will have sometimes a maximum delay, minimum delay, sometimes a typical delay, sometimes the maximum delay as well. Okay, then define single input gate primitives. So what is a single input gate primitives? Single input gate primitives has single input, they have single input and 1 or more output. So these gates have single input but 1 or more outputs. And the gate primitives are, it could be not if, buff if, not if 0, and buff if 0. Also have a control signal. So with respect to the input, they have a control signal. Okay, but the output goes as multiple outputs. So here name of such gates can be given as like not if 0, not if 1, buff if 0, and buff if 1, and as well as the control signal. So in the port list, if you are writing the code, you have to write module gate primitive, module gate primitive. In the port list, you have to mention output ports, output 1, output 2, and the control lines as well. Okay, then the gate propagates only if the control signal is asserted, else the output is high impedance. So here the output is observed, or else the output is maintained properly with respect to the control systems. control signals. Likewise, in the multiplexer, we have the selection lines, right? So based on the selection lines, output is observed. So in the same fashion, based on the control signals, the output is observed. Otherwise, if you are not considered any control signals, the output may goes with the high impedance state. Okay, then coming to the time register. So what is this time register? We all know that registers are nothing but they are the storage devices. They store some bits of information, right? So what is a time register? It is an essential factor in designing the digital circuits, obviously to store the information and also to give the information at respective intervals of time. In the digital circuit designing, this timing controls we have, and it plays a great role, and we need something to keep track of it. So obviously, in order to keep some track, or else what sort with how much of delay the information is passed to the output, or else with how much of delay the information is passed among different modules. So all these things can be considered, or else all these things can be it keeps some track. Okay, it keeps some record. So this timing register, it will keep some record pertaining to the timing and as well as the information passes among the different modules. And then hence the keyword helps us to record the simulation time. So here the default size of time register is implemented specific, but should be at least 64 bits. So here at least 64 bits implementation specific. The time register will contains at least bits of 64 bits. Okay, 64 bits is a minimum number of the storage capacity of this time register. And then coming to the buffer. So what is this buffer is? Buffer is nothing but it is a gate which functions exactly opposite to NOT gate. So buffer is meant for the gate. So here in the single input primitive gates, we are considered the gates which are coming under single input primitive gates are NOT if 1, buff if 1, NOT if 0, buff if 0. So here NOT and buff, they both are the gates, right? So obviously here the buffer is nothing but it is a similar, or else it functions exactly as the opposite to the NOT gate. We all know NOT gate is if it is 0 and 1. If it is 0 is the input, output you observe as 1. If 1 is the input and output you observe 0, right? So this is, that is, it transfers the signal to the output from the input exactly as it is. So we are saying that buffer is exactly opposite to the NOT gate. So this is a NOT gate. NOT gate is if input is 1, output goes for 0. If it input is 0, output goes as 1. But when it comes to buffer, what is this buffer says? When the input is 0, output is also meant to be 0. If it is 1, output also meant as 1. Okay, so this is a buffer gate. And try. So what is this try? Try is nothing but a wire net can be used for nets that are driven by the single gate or continuous assignment. So whereas the try net can be used where multiple drivers drive a net. So try is nothing but actually these are the variables where it connects the devices. Okay, they acts as a wire in order to connect some devices. But here, if the multiple drivers are driving the nets, or else if multiple drivers are driving some variables from the different modules, then in that cases, instead of using wire, we are going for the net, right? So wire is only meant to connect the small devices, okay, small network. And for the small network kind of things, we are making use to connect the wire. Okay, with the help of wire, we are connecting all the modules, okay, all the gates. But if you are considering, or else if you want to connect some if you want to connect the devices from the multiple drivers, okay, from the multiple drivers, if the devices or else the modules, if they are, if the connection is needed, then obviously the try is a net we can make use. Then, so a wire net can be used for nets. Okay, a wire can be used for net that is driven by a single gate or continuous assignment. Or if only single driver, if the variable is driven by a single driver, then we can obviously make use of a variable net called wire. Okay, if that's not the case, that means if multiple drivers are driving a net, for example, then in that cases we can make use of this try net. Okay, try is a net where we can make use of it when multiple drivers are driving the net. Then coming to the wire. Wire is nothing but it's a keyword. The most commonly used net in modeling circuits. So it's a most common. For example, I'm modeling some device. So in order to model some device, what I need to do, I need to interconnect all the gates, right? So in that purpose, I'm using a wire. So this is nothing but the wire. Wire is meant to interconnect the devices. So here it's a keyword mostly used net in modeling the circuits. we use when used in the code, it exhibits the same property as the electrical wire used for making connections. So here in the code, when you are writing the code, we will write like wire A and B. That means what? There is a connection between A and B. That's how the representation goes on. So it is a basic keyword just for the making connections. We'll make use of this wire. Then define net. So what is this net? Net is a data type. In the Verilog, there are few data types, as well as also in the C language. When you compare the C language and the Verilog language, there are many similarities if you will find in both the languages. Though C is a software concerned language and Verilog is a hardware concerned language, but the similarity, the terminologies can be are almost same. So here, nets are the data types in the Verilog that represent the connections between the hardware elements. So obviously the nets are nothing but the data types. So under nets we have registers, we have wire, we have try, and we have wire. Okay, we have tree reg. So these are nothing but these are all comes under net. So these are meant for the connection purpose. So that means what? Using the register, or else using the I can connect the multiple drivers. Using a wire, I can connect a single drivers. Using the tree reg, I can connect the multiple drivers at a time. So likewise, nets are the data types in the Verilog, and that represents the connection between hardware elements. So in order to connect some gate, okay, NAND gate and OR gate, in order to connect some the connections between the hardware elements can be easily meant with respect to the net. And nets don't store value. So as these are the data types where the nets are the data types, they don't store any value, they just pass on the value, or else it acts as a connection kind of thing. It acts as a wire. For example, if you want to, you'll observe, you have some wire, right? So what does that wire do? It just connects the two devices. So they, that's the reason we are saying that the nets, these data types, they don't store any sort of values. And they have the values of the driver. So as they don't store any sort of values, but they store the they store the values of driver. Drivers are nothing but, for example, see, this is what I am connecting. Okay, AND gate, OR gate, and XOR gate. So here with I have a value 0. This driver, with respect to this driver, it is driving with respect to a signal strength of 0, and it is driving as per the 1. Okay. So likewise, they have the drivers. The drivers will have the values, but the wires or the connectors they don't have, or else they don't store any sort of values. So these are nothing but the nets. And so this is about the definitions that we come across in the module 2, gate level primitives, and all these definitions are easily and very important in order to write your exam, or else in order to write how to write a code based on the different categories. Okay, so these are the single primitives, user defined primitives, and as well as connecting connectors, tree reg connector, try connector, wire connectors, and these are coming under a one roof. That is nothing but a nets are nothing but the data types. And also we have discussed about the delays, and delays are pertaining to the input and output. With how much of delay that you are observing, the same kind of delay you will observe the output. And in the delays we have discussed about the three different delays: rise delay, fall delay, and turn off delay. Rise delay, if the transition going from 0 to 1, it is nothing but the rise delay, and the transition going from 1 to 0, it is nothing but the fall delay. And the transition is going either from 0, x or z value with a 0, x or 1. Okay, 0, 1 or x with a high impedance state. If the transition is taking place from 0 to z value, or 1 to z value, or x to z value, if it is going with a high impedance state, then that sort of delay is nothing but the turn off delay. And also in the representation, we have 1 format of representation delays, 2 format of representation, and 3 format of representation. So if you are going with the 2 format of representation, in the coding you have 2 delays, right? One is with respect to rise, and one other one is with respect to fall. And if you are going for 3 delays, you have rise time, fall time, and as well as the turn off time. So this is how the representation goes on. And then there is a major differences to be, not major differences, there is a differences to remember Okay, which is more important to remember the difference between the edge sensitive and level sensitive. In the level sensitive, the output is observed as it is, but whereas in the edge sensitive, we'll have one more next state can be observed, and that state is mentioned in the table. Okay, in between the table and end table, we need to mention the next state output as well. Okay, this is one of the important point to be remembered if you compare both level sensitive and as well as the edge sensitive. And then UDPs and combinational UDPs, the number of maximum inputs it could be of 10, and then sequential UDP, they are 9 inputs, and they are the symbols and the comments as well. And also that's it. So I hope you all understood the definitions well in this module 2. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.